an educational series on cybersecurity, compliance, and IT governance. Produced with the support of Freedom Technologies, Phoenix's leading managed service provider.
This is a topic, though, I will say this talk is kind of a beta version. I came across this about a few months ago, so I'm not super well read. I've digested a few major papers, some of the big ones. I feel this is one of those things when you learn it, feels like you should have already known it. I know I felt kind of incompetent, even though I've done this for about 24 years. Since 1997, I've been doing computer stuff professionally. And having only learned about this recently, it's just, like I said, it's one of those enlightenment moments that it's like, wow, this should be in every school. You shouldn't be allowed to get a degree or a cert without understanding this. So the first place I heard about weird machines was a gentleman out of the UK. He's done some really interesting work for the British military. And we had him on the podcast we were doing for a little while, the second version of that. And he threw a whole bunch of these terms and planning methodologies and testing methodologies and everything else at us. And he was like, you should look this up. You should look this up. And I'm like, wow, that's like 3 years worth of research. That's awesome. So I didn't. And then a few months later, I was writing something up. There's a new term called LangSec that we'll get to, or language theoretic security. And I found that, and I found weird machines through LangSec, and then I started digging into that, and they're both related. So this gets to the heart of what is an exploit. If you've ever wondered, hopefully we'll answer that tonight. So let me jump right into it. So the title of the talk is, That's Weird. I Thought I Secured That. And this is an intro to weird machines and the nature of exploitation, and how might we actually prove invulnerability of software. Because this is something most people think is impossible. It's actually not. It is actually very mathematically possible, and there's quite a bit of work going on in the last 7 years. So let me get my speaking notes up for me. So right now, and I wish I could do some screen sharing. Right now, everyone's familiar. We were just going over, and that's a fixture of this group, is the different hacks that we see all the time. There's that wonderful visualization with the little bubbles, and I actually managed to screenshot that. And you see 10 years ago, especially 20 years ago, hacks were extremely rare. Very few records were compromised, and it wasn't a big deal. You know, it happened pretty infrequently, and it really made the news because it was what, once every, 2 to 5 years. And part of that is another talk/paper I've been putting together talking about friction and damping. And we have this idea, and just to give the teaser of that one, that oh, let's connect everything. Everything's better when we connect everything and we reduce friction. That's amazing. And that we should just do that to all the things. And especially with COVID, we learned that supply chains, making them super efficient, has some major downsides. So once you connect everything, you don't have any damping. So once a failure starts, it propagates very, very quickly. And it can spread to other systems that shouldn't be related, that suddenly those can be taken out. And so you have also the speed, like we saw the Ethereum flash crash. The entire Ethereum currency several years ago, there was someone sold a little too much. I forget what the initial trigger was. The entire currency dropped to 0 and then bounced right back up. Before anyone could notice, in under a minute, whole currency went to worthless and then bounced back up. Now, I guess it's kind of good to bounce back up, but it shows you how volatile systems are. When you connect lots of things and you don't have any kind of damping, you have problems. And we've done that more and more. Again, 20 years ago, 30 years ago, no one ever heard of a huge medical records breach, right? Sure, there was espionage, there were people stealing records, but when you have a file cabinet that's this tall, you can't go ahead and you can't, just show up and steal all the data. It's going to take a while. You're going to need, depending on the size of the office, a whole bunch of trucks, and you're going to need a whole bunch of people to move that much data. But once you reduce the friction, you can exfil all the medical records very, very quickly, not instantly, but close enough, and before anyone sees it. There's also less visibility with electronic systems. So anyway, that's a separate talk, so I'm not going to waste any more time there. There's these laws of software. There's a really good GitHub repo called Hacker Laws. It doesn't have this one. I need to do a pull request or someone else can beat me to it. But who's heard of Sturgeon's Law? So I think it's Ted Sturgeon was a science fiction writer. Sturgeon's Law is 90% of everything is crap. And the point he was actually trying to make is that, yes, most science fiction is really bad, but there 10%-ish that isn't is really awesome. Now, in computer science, the number is probably a little bit more generous. It's probably a lot higher than 90%. But yeah, there's a lot of stuff that is terrible. Most stuff, I would say, probably 99% is trivial to hack. It's full of holes. But there is this growing maybe 1%, and some of this goes back to like the 70s and 80s, that is really interesting and really well, like mathematically precisely designed. So given all this, we need to find a better way. It's clearly not working. We're seeing breaches go up in size and sophistication. And we've tried adding more and more layers. We've tried bringing in more complicated stuff, bringing in AI, bringing in ML, bringing in all this other stuff. It's not making it better. It's making it worse. So how do we actually do that? So a little feedback here. Someone needs to mute.
I'm going to mute James Stewart. There we go.
Hey, okay, cool. So, so most people, let's talk about what is a program. And this sounds pretty elementary. And most people have this idea of programs are this factory. And so you have this factory and data goes in the factory and the factory processes it like raw goods, and then process data, new products based on the data come out. And it's not entirely wrong to think of it that way, but it's also not entirely accurate, because what we fail to realize is the control flow, whether you're talking about if statements, if else ladders, switch statements, pattern matching, etc., all of these things, the thing that triggers those to happen is the input. We're saying if this happens in the input, then go down this branch. So there's really kind of an inversion there where the entity driving the code, it's not the person that wrote the code. They don't really have any control anymore. Whoever's providing input is actually driving this system. And because of that, well, if you get to drive, unless you're kind of on rails, well, you can drive it wherever you want. And that's kind of the key thing. If you read the original Brattis paper proposing weird machines, once you control the input, you can do weird stuff. You can find these weird behaviors and really work toward having a weird assembly language. And so now you're inside this machine. There's like a little other computer hidden inside the main computer, and you can start to figure out how to program that. And you can use buffer overflows, you can use timing-based attacks. There's a whole and large and growing set of ways to find these weird machines through kind of black box testing and learn how to program them, and then assemble all of this into basically just programming a different machine, but a hidden one. And so this goes to the heart of computability. And people mostly talk about Turing completeness. There's some other formal ways to talk about what is computable and what are the limits. But ideally, we want a system, this little chunk here, and that's it. And that machine should do exactly what it's designed to under all conditions. And that's it. It should never do other things. It should never get weird. And the problem is, as you make things more complex, there's more flexibility. And these little weird machines expand the amount of computability. What you can do just keeps growing. And the more layers you start adding, the more stuff you can do with the weird machine. And this goes back to in the early days of some of this research, they were saying, well, there's no way to get the machine to do a thing that the designer doesn't want you to do unless you bring your own code. So we're going to have to find a way to like bring our code onto the machine. And as we're all well aware now, you don't actually have to do that. You don't even have to do code injection. You can actually build in this little weird machine through what they call weird assembly instructions, a whole exploit. There's enough capability in most modern machines that you can build whatever computation you want. It's a little bit less efficient usually, but there's still plenty of computational power and freedom to go ahead and build whatever you want and make the weird machine do whatever you want within this larger system. So given that, how do we deal with this? Well, if the input is the problem and the input allows us to drive wherever we want, then could we restrict the input? And yes, we can. Most people don't do nearly enough input validation, and validation's fine, but there's a great article, Parse Don't Validate, and it talks about how much information is left. And so what we actually want to do, if we take a parser, then we can put a parser, if there's any security critical like boundaries between major components, because we don't want to go nuts if you start injecting parsers between every component, that's obviously going to add too much overhead. But if there's major system boundaries, we can start adding components like parsers between these, and we can start thinking about the input as a formal grammar on the Chomsky language hierarchy. So hopefully everyone is familiar. If you're not, the Chomsky hierarchy starts with type 0 and goes to type 3. Type 0 being context-free, like fully unrestricted. And I've seen different gradations. I think type 0 through 3 is, I think it's basically accepted, but I've seen sub-categorizations up to like 6 or 7 levels. So most people are somewhat familiar with type 3 languages, which are regular expressions, and they're pretty limited. I think there's one level below that's even more constrained, that you don't need any memory to evaluate. And it's basically how much compute do you need to be able to parse these languages effectively. And this, as a slight aside, goes back to the whole idea of, can you parse XML with regular expressions? And formally, mathematically, no, you can't. It's mathematically provable that regular language cannot be parsed, or excuse me, that a recursive language cannot be parsed with a regular grammar. It's impossible to do. You can do snippets of it and not screw up 100% of the time, but can you take any input and can you turn that into a well-formed data structure? No, because you're trying to go up the hierarchy. And as the level gets smaller, there's more flexibility, there's fewer constraints, and therefore you need a more sophisticated parser. So anyway, small bit of trivia. But we can go ahead and we can take input, and even if it's just bytes and bits and we're using, you know, binary formats, we can still define this as a formal grammar that has formal rules. And we can take this huge input space that is close to infinite, never obviously infinite because our machines aren't, but enormous. And we can take it and cut it down and say, no, no, you're only allowed to use the stuff in here. Just like with English, right now, I love George Carlin's thing. I forget the words he uses. He's like, say it in your own words. And he's like, make up your own words. He's like, I'm using the words everyone else is using. So that's kind of what we're seeing with weird machines, is people are essentially making up their own words. They're finding a new grammar that they can feed to this weird machine to get it to do stuff it was never designed to do. So if we can prevent those words and say, look, only these words with these rules are allowed in, then now we have something where the input space is constrained and it's much, much harder to trigger weird behavior. Now, I can't totally see the comments right now, but I'm going to guess that if someone hasn't already typed it in there, the first thing you're going to say, because this is my first thought too, is, well, I'll just go after the parser then. Fair point, except there is actually one paper, I haven't seen more than the one, but there is one paper showing that you can actually make a parser that is provably, you can't really attack it, like the amount of behavior and computation is constrained, and you actually, and I can't remember, if it was Bradis or Dullian, these are two of the big names in the field, and there's quite a few more joining the fray. But yes, you can actually ensure, if you take the time, that a parser is not vulnerable to weird machine behavior itself, because obviously that would be a loophole if that weren't true. So that's one thing we can do. And to me, I have a toucan graphic, I call it, showing the different levels where we started with just totally unconstrained, and we started adding firewalls, and we started adding web application firewalls that take a little bit better look, but are still pretty coarse. And now the big thing is what zero trust architectures. I've got friends on LinkedIn in other countries that are selling, oh, zero trust, zero trust. It's great. But zero trust architectures, again, they are like maybe halfway to where we need to be. And they're still way too coarse. So now you're allowing everyone to authenticate, or excuse me, forcing everyone to authenticate every time. Well, that's great, but once they authenticate, they can still feed gibberish in. So LangSec to me is beyond zero trust. Now we're finally being able to like constrict the input space and say, no, no, you're not even allowed to say gibberish. You can only say things that make sense to the computer, to the machine that we intend you to be programming. So is that it? Can we go beyond that? Are there still any other types of bugs? And the answer is, sadly, yes. There are still logic bugs. So there, and we've seen flaws. I don't have an example off the top of my head, but we've seen flaws in authentication systems. Actually, this may not be a perfect example, but the Apple bug, they had a switch statement that was improperly terminated in iOS about a decade ago. And it would let you kind of fall through and authenticate when you should not have been able to. So that's a logical problem. That's not a matter of the input necessarily being the problem. You can send it valid inputs. And I've seen other, like, I remember early in my career building websites, one common mistake people would make is they would fail to validate, to check, is the password blank? And there were some early web apps back in like the late 90s where you just put a blank password, hit return, and it would just bypass all the checks. And it's like, yeah, you don't want to do that. You don't want to let someone in with a blank password. That's a terrible idea. And I hope we've gotten beyond that at this point. But yeah, there will always be logical bugs. There will always be, if we think of a program as a state machine, there will always be transitions between different states that we do not want to happen. So that's the next level, is can we then stop those transitions? Can we prove that a machine can never transition from a state that makes sense and get into some weird, inconsistent state that is just makes no sense at all and allows an attacker to start doing things that weren't intended? And that goes back to stuff we've talked about before, formal methods. There's a number of different techniques being looked at right now. There's type systems are a great way, depending on how nutso you go with the type system. If you're talking something like Rust or Haskell, then you have some flexibility. You can stop certain types of errors. There's actually a really cool Rust library that at first definitely raised an eyebrow for me. There's this, what's the name right now? You know how you're not supposed to do string concatenation with SQL? That's a terrible idea. You are begging for an injection attack. There's actually a Rust library that, because of the way Rust handles strings, and they can see between like a dynamic string that's coming in from the user or a string that's like basically just stuck in the string section, of the executable that's compiled in statically, because they can make that distinction, they can automatically, when you just concatenate these things together, they use type signatures to say static strings are fine because those are hard coded into the program, those aren't a risk, but everything else has to go through this other function to be converted into something that can concatenate with a static string, and we're going to escape it. So with a powerful enough a type system, you can go ahead and you can concatenate strings and not worry about accidentally falling vulnerable to a SQL injection attack or any other kind of code injection attack. So that's pretty neat. And that's not even a very powerful type system. There's plenty other stuff out there. There's Idris, there's Coke, there's Isabel, there's Synquid. Sadly, the demo's down, but Synquid is using a full dependent typing system. And for those that are unfamiliar, this is saying the type is not just the type you say, it's not just a number, but we can have arbitrary predicates. And so we can say, I want to allow this function to take natural non-zero numbers, which is super handy if you're dividing. If you have a divide function or a div function, right? You pass in a 0, you get a hardware fault. The processor's like, what? I can't do that. That makes no sense. And you get a hardware fault if it doesn't crash out earlier. With a dependent typing system, you can actually say this function cannot take a 0. So now in the code, we can go ahead and we can restrict and say, here's the safe domain that this function can operate in. And we will reject anything that falls outside of that. We will say, just no, we're not even going to take that. And some of this can be checked at compile time. You can make sure everything's wired up. Obviously, with dependent types, you can't do all your checking at compile time because you don't know what the values will be, and thus the type signature until runtime. But it's really neat because you kind of get this automatic dispatch where it looks at the code and you just set your type signatures up in one place. And then any function that takes the type signatures can say, well, wait a minute, does this match up? Can I even safely accept this type signature? Or, I'm not even going to try to do something weird because I know I can deal with all the values that are greater than 0 that are integers. I know I can handle those properly. And that just totally shuts down the ability to sneak in some little decimal value or something. So there's a great talk, by the way, about 5 years ago-ish. So he was at Stefan Edwards gave a talk at Cactus Con back when it was downtown. And I saw a good comment from Nancy. Yes, I'll get to that in a second, Nancy. So Stefan Edwards gave a really good talk about encoding your security model, like actually working with programmers using more advanced languages and building the model, the actual authentication model, not just authentication, but the entire security model into the type signatures so that you're not going to miss anything. Because the great thing about types versus putting it in some file, having like an authorization file, is types, the compiler automatically double checks everything for you. And if you make a change to a dependent type signature and say, oh, also reject these values, or, oh, now we know how to handle these, go ahead and accept these too, you're not going to miss it anywhere. That gets incorporated into the code by the compiler. There's no like, oh, we had 10 places this function was used, and we have to check if we're handing it valid stuff at every place. And oh, we forgot. We switched 9 of them and we forgot 1, which leads to a fun little, not quite an actual Heisenberg bug, but something that's really fun, wastes probably a few weeks or months of your time to track down and figure out what the heck is happening when it only fails maybe 1/9 of the time, assuming a even distribution of function calls, which is not usually the case. So, and I've seen stuff like that in production. I've wasted more of my life than I care to admit tracking down stupid stuff like that. So as a programmer, I really like the idea of having the compiler have my back. Like Rust has been amazing, where I tried to link in libgit2 into pass it in basically to this web server, which was multi-threaded. And Rust is like, no, absolutely not. Like that's going to be a bad idea. That's not reentrant. You're going to end up with bizarre threading issues that it's going to be just god awful to track down. Just, we're not compiling, try again. And at first you're like, dang, why isn't this compiling? But then you realize, oh, wow, this compiler, unlike the C compiler, is not just punishing me arbitrarily. Like there's a reason it didn't let me do that. And this is actually saving me. I'm paying a little bit more upfront, but it's saving me a ton of time down the road. So I want to respond to that comment about Ada. And there's Agda, there's Ada, there's some of these that actually go back quite a ways. And so this isn't new ideas. This is honestly the most depressing thing about this whole fiasco that is modern computing. We kind of knew some of this. Some of this is brand new research. Weird Machines, like I said, I think it's maybe 10, 15 years old. Langsec, they've only been having conferences for the last 7. So some of this is relatively new, at least formalizing it and really getting it out there as ideas you can search and find resources on. But yeah, there's stuff like Ada. There's a really, really good talk. I have like 4 talks right now. Actually, it's probably more like 5 or 6. I don't have the thing complete. And eventually I'll put this up on our website. But there's talks that you should, if you're in computing, especially if you're a programmer, but also just generally if you're in computing, these are talks you really should watch. And Carol Nichols, I believe, one of my newest favorite ones is Rust, a language for the next 40 years. And even if you don't care about computing and technical stuff, watch the beginning, watch the end. She talks about the brakeman. And there, if you ever looked at the old style trains and you've seen this little walkway and you're like, wow, that looks like a walkway on top of the train. But I thought people only walked on top of trains in movies. That seems like a terrible idea, walking around on a moving train. It is a terrible idea. And people used to do that. And it used to be one of the deadliest jobs in the US. You had people running around, the brakemen, who, when the conductor wanted to slow the train down, would have to like hang out the window, hey guys, stop the train. And they would run across the top of the train from train car to train car, cranking down the brakes. And it took a while to stop a train. And there were derailments because they couldn't stop in time. They would miss stations where they just didn't manage to get all the brakes locked down quickly enough, and the train would actually pass the station, and all the passengers would have to get out, and they would have to, walk back to the station through the mud and the dirt. And people got tired of it. And eventually Westinghouse invented the air brake. And at first they laughed at him, which is, again, what I'm seeing a lot of in programming. Oh, these ideas are stupid. They don't actually work. We tried those a while ago. They didn't work. We gave up on them. We're just going to try other stuff. We're going to more and more layers to make our stuff secure. And, now we're seeing that doesn't work. And just like we saw at the railways, what it took was actually passengers. And they said, wait a minute, what? There's a brake that the conductor can actually, they can instigate a stop of the train. They can engage the brake with one person, and all the cars brake at the same time. Well, that's really cool. Like, they probably wouldn't miss a station then. We want that. And not to mention the number of brakemen. If it's windy out, if it's rainy out, if it's icy out, you lose a few people. And that's what we're seeing now. John mentioned Kaseya. We're losing a lot of people. I have my other talk that I actually, some of you may remember the Doomsday Machines talk. Anyone remember how many deaths were directly attributable to software, at least the ones that are publicly disclosed? Because there's some that aren't in the talk that I can't share. And I'm sure there's plenty more I have no knowledge of that are out there too. Back then, I think we were, I can't remember if Boeing had happened. We were at a few hundred people. We're up to almost 2,000 now. So I will be giving an updated version of that as a professionally produced video talking about all the different things. And there's some new ones that have happened. There's Boeing, all that. And anyone who's followed the Horizon incident, that hasn't killed anyone per se, but it has led a whole bunch of people in England, almost 1,000, about 750 or so, to be, some of them, imprisoned for 15 years because of a bug. So this stuff is getting real. Like, we've had this wonderful run where for the most part, didn't really matter. I mean, we saw some space probes, right? They screwed up the from feet to meters, slammed into Mars, lost a few $1 billion there. We've seen some other big costly incidents like that, but the businesses, we've all gotten reliant on, oh, we'll just pay for the insurance, and yeah, it's just a monetary thing. No one died. Well, almost 2,000 people have died now. And I'm guessing within the next 5 or 10 years, those numbers will continue to go up. There was just, I don't know if this was mentioned earlier because I joined a little late, but there was just a train system lockout in, I'm blanking on the country right now. It's just on Hacker News yesterday, but they did a wiper attack and they wiped all the computers, and the entire train system is, oh, it's killing me. I can't remember the country. I'll have to look it back up. But yeah, major transit denial of service. So think of the ripple effects. Think of how many things people can't get where they need to go. If there's organ transplants, if there's freight, if there's whatever else, all of that, the cascading effects of having the train service shut down by some other party, like, this is getting serious. We need to stop screwing around. So Carol Nichols, watch Rust the Language the Next 40 Years. There's another wonderful talk going back to Ada, Gresham University, I believe. And oh yeah, and someone's mentioning in the comments, WannaCry. Yeah, they had some hospital. There were a few deaths actually, I believe, in Europe. I think Germany. I think England as well, with some of the ransomware with medical equipment. That isn't in my talk, by the way, because Doomsday Machines is about mistakes, just whoops. So to me, there's been plenty of incidents where there's malice involved and it causes a ton of damage. And to me, these are two separate categories. Like, whenever you see on the news, they're like, oh, we weren't hacked. We weren't hacked. It was just, it was a bug. It was a mistake. I don't know about the rest of you. I am much more terrified of that answer. I would rather it be an attack, because if it's an attack, there's a human you can reason with, and you can say, well, wait a minute, like, please don't, or here's the money instead, or, we still have nukes. Maybe don't attack us anymore, which is not a great idea. That's a separate talk as well. So there are ways to deal with that. To me, it's even more insidious and terrifying when you have, it just broke. There was no malice. There was no one intending to cause these deaths like Horizon. No one was like, oh, these postal workers, I'm going to get them. I'm going to ruin, almost 1,000 of their lives and lock them up unjustly. Someone just screwed up. And someone wrote software that found fraud where there wasn't any. And it ended up destroying almost 1,000 lives. So that's worse. I would much rather have this be an actual adversary. Oh, yes, Nancy's on it. Train system in Iran. Iran was the one I was mentioning, the wiper attack. So anyway, I would rather have it be something like that, because a lot of these attacks can be mitigated relatively easily. When your code is just so broken that it's a death trap, to me, that is, and I'm honestly surprised at how quickly everyone forgot about the condo in Florida. For a while there, we had a lot of people, how did this happen? Buildings don't just fall over, right? Because we do have good building standards and they're pretty well enforced, well, outside of Florida. So it's about time we had that for software as well. And again, have we seen this? Everyone immediately goes to, it's too expensive. We can't afford to do this. So there is a Martin Thomas out of Gresham University. in England, wonderful 1 hour talk on correct by construction software. And I believe the company is Praxis, if I remember correctly, and they use Ada Spark. So Ada goes way back, and there's a 2012 variant of Ada, which a certain set of features, they actually kind of rewound to 2012 and said for Spark, we're capping it here. And then what Spark is, it's a set of extra tools that you can use on top of Ada. Because an issue you run into, if you look at something like MIT's Alloy, which has been around since the late 90s, TLA Plus, which is Leslie Lamport's work that Elasticsearch has been using, they had some really nasty little bugs that they had these clusters, petabytes, multi-petabyte clusters. So enormous amounts of traffic and data and compute going on. And they're looking at the numbers and they're like, guys, you got bugs, like fix them. And they're like, well, okay, 5 petabytes, how many racks, how many disks? Like just trying to replicate that bug traditionally, it's going to be millions, if not tens of millions, just to set up and then try to synthesize or collect the data set to try to reproduce this intermittent bug that it just doesn't make any sense. They don't have that kind of funding with Elasticsearch to blow millions on one bug. So what they did instead, they said, well, wait a minute, let's model the actual algorithm we have. And let's look at all the different state transitions. And TLA Plus is really good at showing discrete time steps. So these things are in this state, and then they transition in the next time step to this state, and then they transition to this state. And TLA looks for places that you found that you have gaps, where it's like, well, wait a minute, that doesn't make any sense, or now these are in conflict. It's a really wonderful system for finding those little logical flaws in a protocol that if you're doing a consensus protocol, which no, it has nothing to do with blockchains. We're talking Paxos, Raft, legitimately useful consensus protocols, not lottery BS from blockchain, but again, another time. How do you know it actually works? These things can get very complicated, and it gets even more complicated when you think about global systems and you think about relativity. Even if you manage to sync all the clocks, that now that we have super accurate clocks, they actually confirmed Einstein's theory of special relativity. They threw an atomic clock up in a plane, flew around at high speed, landed, and just like we expect, we see a tiny bit of time dilation. Not enough for a human to notice, but when you're dealing with massive systems with petabytes of data with billions of global users, definitely enough to throw off the consistency of the system. So even assuming you can actually sync up all the clocks, you're always going to have time dilation at the equator versus northern regions. So you will never be able to keep a clock precisely in sync from Norway to Hawaii. That just physics is against us there. So anyway, this whole separate thing of computer science on vector clocks and how do you synchronize stuff in a massive global system, but a lot of good research. It actually can be done. So TLA Plus is great to find this. The problem is when you find this, then, okay, we have a little TLA Plus model saying this algorithm works perfectly. There's no flaws that it found. It's great, cool. But we got to get that in the computer. We got to then rewrite that algorithm in code. And then that code is generally going to be interpreted or compiled into code 1 or 2 layers down. We're going to take the human code, go to, probably in an intermediate language, either an IR or down to machine code, and then down to assembly, et cetera. So there's several steps where mistakes could be introduced. So the actual algorithm running in the cluster is not this beautiful, pristine algorithm that never fails over here. It's close, but not the same. So that's been a major stumbling block of how do you make sure that the proof and the actual implementation match up. And in circuit design, in electronic design automation software, EDA software, which is actually where I kind of started my career, there's a thing called layout versus schematic, or LVS, because you have this schematic of logically how all the pieces, all the little transistors and diodes and all this connect to make the logical circuit work. But then you have to fit all that onto an actual chunk of silicon when you design the mask. And these had been separate things. And actually, one of the things I'm pretty proud of is the company way back in the day that I worked at, one of our innovations was to take what's called MVC, model view controller in programming, where you have a mathematical model, kind of your back-end code. And then you have different views that take some of that and visualize it so that the user can see what's going on. And then you have controllers that when the user does something, it routes to the right place, and it goes ahead and it dispatches and makes the changes to the view, and then it re-renders it so the user can see what happened. So when I was very new to programming, I learned about this. I'm like, oh, this is really cool. We could have multiple views. We could have a 2-dimensional, we could have 3-dimensional, we could have like, there's all these different ways with the same model. We have the data, the source of truth, and then we can project that out a whole bunch of different ways. So why don't, instead of having the layout here and the schematic here, and then have the software that has to basically just go through and manually, but very quickly check, does this match that? Does that connect to that? And, and do all this work. Well, wait a minute, let's just use one model. And then there's no way that these two can ever get out of sync, because when you make changes, you're both changing the same data set. So all the logical, like what connects to what, you're just looking at it in different ways. You're looking at one that's a logical view and one that's an actual spatial view in 2 dimensions, and you can't lose track of it. And so this is what Ada Spark gives us. So some of these ideas, again, not new. Ada Spark lets us write code in Ada, which there's a wonderful PDF came out less than a month ago called Ada for the C Programmer that is really, really cool. And having read about Eiffel and Haskell and Idris and Coke, all these other things, Ada, I'm gonna say I'm jealous. You're reading through this and you're like, oh, you can set preconditions. You can set, and we'll go to the old Eiffel example. So if you're making bank transfer software and you want to make sure that I'm going to transfer money from this account to this account, well, like we want to make sure before we transfer the money, first of all, are both accounts active? We don't want to be transferring to or from an inactive account. So those are some preconditions we want to check before executing the transfer, the body of the transfer method. The other thing we want to do is there enough money? If I'm asking to transfer $5,000, does the account I'm transferring from have $5,000 in it? And then we also probably want to say the target account and the source account, let's sum those up and save that for later. How much total money is that? Let's save that over here. And then we can go in, we could do all the stuff we got to do to make the transfer happen, assuming all the preconditions are good. And then afterwards, we can have post conditions and we can do sanity checks. And we don't need to check if the accounts are active because we did that already. But now after transferring the money, we can take the two new balances, add those up and say, does the sum total of the money in these two accounts that we just did the transfer from match the saved sum from earlier? Because if it doesn't, money either disappeared or just winked into existence. Something is horribly wrong. So this can be built in to the code and not just run as separate tests occasionally, in a continuous integration setup before you deploy just, oh, we checked a few things. But this can actually be part of the code that runs all the time and ensures that nothing, out of bounds. If something got weird, this pulls it back into a normal state. So very, very cool. There's a whole bunch of other features of Ada Spark. And what Spark does is that cool proof stuff we were talking about in TLA Plus, we can do that in the exact same language. And we can kind of bind this all together in addition to the pre and post conditions and all the other cool stuff that Ada lets you do. We can now combine these two and we can have the system double check everything. And you have all these assertions about, this code. Is it correct? Does this hold? Logically, is this coherent? And now that we have that, and we can have the machine double check everything, so we're not going to miss it in a code review when we're tired or we had too much caffeine or whatever. That's a really powerful thing. And the other thing worth mentioning is, a lot of people, Bob, Dr. Bob, I can't remember his Bob, not Martin. Anyway, there's Uncle Bob is what he goes by online. He's big. Oh, you just got to try harder. You just got to be a better programmer and pay more attention. There's limits to that. Like you're gonna miss something. It's not about being a better programmer. It's about having tools that actually help you out rather than get in your way. Like it's basically impossible to write C code. If it's more than 10 lines, if it's non-trivial C code, I don't care how good you are, you cannot write code that you can guarantee works properly. It might on one compiler, maybe. But then if you compile it somewhere else, or you make some other small change, or you change a flag, if you have the preprocessor, that's one of the arguments against the preprocessor. You're literally compiling completely different code bases. It's just cutting and pasting essentially based on what defines are there and what aren't. So having such a rudimentary preprocessor does not allow you to actually validate that it all makes sense and that the code paths are all valid. You can do some really stupid stuff in there. And that's where you see a lot of, I'm looking at John's thing, state machine stuff. I was just trying to see if he was arguing that you could do some computation in the preprocessor, but no, it's not like Rust, it's not like Lisp. where you have the full expressivity of the language in the preprocessor, right? Like having a proper macro system is a beautiful thing, and C, among the many failures of C, it's just there to sabotage you. C, the analogy I use, it's kind of like Rust is the dad that's looking at the kids, got the jump set up, and he's like, no, sorry, no, I'm not gonna let you jump. You need to put the helmet on. You need to put, elbow pads on, and that jump's gonna fall over. You need to make sure it's actually secured, where when you hit it with the bike, you're gonna go over it, not just knock over the jump. Whereas C is like the dad is just like, or I guess the irresponsible uncle, go for it, buddy. Let's see what happens. And it's amazing what you can get to happen either intentionally or unintentionally in C. So I'm not a fan. I did a lot of my early programming in C++, and you can drag me back there kicking and screaming. I will never willingly, of my own accord, write C code again, because there's too many undefined corners in the language. And that goes to what we were talking about with testing. One of the truisms, testing can prove the presence of bugs, but it can never prove their absence. And we see that all the time. There's a wonderful library in Haskell called QuickCheck that's been ported to 30+ languages. And the term now is property-based testing is the accepted industry term. QuickCheck is the library. And what it does, it's basically fuzzing. And so you take a bit of code, and QuickCheck will just throw random crap. It has a generator function and a reducer function, and it'll just throw crap at your function, and it'll look to see what fails, just literally random values all over the place. And then based on what fails, then it tries to use a reducer to find the actual, like, what cases are actually causing this. Is it failing when the number is odd? Is it failing only when the number is above 20,000 or over 9,000? Is it failing only when the number is negative? Like it tries to then reduce down the set of failure cases to the actual property that's causing the failure. So again, very cool. QuickCheck is definitely better if you're going to be testing your code. QuickCheck is a great way to make sure you have comprehensive tests, and it usually uncovers tests where you never thought to test that. But the problem is it doesn't mean it hasn't exhaustively tested every possible thing that can happen. It's just done some crazy, totally random stuff. Since humans are bad at entropy, it'll find stuff no human would. So again, going back to Ada, it's another great article about a guy who was going to teach a class in Ada Spark. And he started off as a low-level C programmer, and he actually made some snide comment at one of the trade shows. He's like, oh, yeah, Ada stuff, it sounds cool and all, but I got real work to get done here. I need to be right on the metal. I need high performance. Like, it's just, I got real work to do. That's a toy. And one of the salespeople was like, well, I don't know, you should check this out. And he looked into it and he's like, that's kind of interesting. And he finally kept looking into it and started using it a little bit, and got to a point where he's like, you know what, I'm going to teach a class. And he was still not really well versed, but he had done some programming. And he's like, all right, let me set up an example of an algorithm. We'll just do like a really, really easy, I don't remember, it was factoring or multiplication algorithm. And we'll set this up. It'll just be brute force, just really naive algorithm. And then we'll prove that it works. And then we'll inject some bugs. And then we'll show how the prover catches those bugs to show the students that, look, this actually does work. It actually finds problems in your code. So he got to step A of build the code, and then, or excuse me, step one. Step two was then prove that it works. And he had already tested this. He had built the code and he had run a whole bunch of numbers just by hand to prove that the algorithm, some little ones, some really big ones. And it comes back and it says, Spark's like, nope. It says that doesn't work. It doesn't work for 1 and it doesn't work for 9. Your code's got a bug. He's like, what in the heck? Like, why would it not work for 9? So he tries it, and sure enough, it crashes. And he's like, well, I mean, that's even better than artificially introducing bugs. This seemed like a very straightforward, naive implementation of this algorithm. And it turned out it had a bug for 2 different values. And Ada Spark was able to find that. So again, the Gresham University talk, he has some really good numbers in there, good anecdotes, but then hard numbers on when you apply, and I'll get to the Copilot thing in a second. I saw that comment and I definitely have thoughts. So when you start using these methodologies, You know, and this is not a new thing in some areas. Air traffic control scheduling systems, the NSA for door locks is one of the ones in the talk. So the NSA has lots of money. So they said, you know what? We're kind of interested. What if we'll have you guys at Praxis, go ahead and build this lock system from scratch in Ada Spark. And we'll have this other group that we're familiar with, and they'll just build it using normal tools and methodologies to our standards. So they did, and what they found was that the system in Ada Spark took them 1/3 the time to build it, and when they delivered it, no detectable bugs on delivery. I think they shipped one minor update. There was one minor feature change that needed to happen, and so they shipped one patch, and that's it. The air traffic control system that they did, so the problem with Heathrow Airport, your limitation on how many planes can you get in and out of Heathrow at the same time, is they're still using analog radio. All the planes, I mean, I guess, again, given how poorly the rest of the computer stuff is, like, in theory, I'd love to see us go to some amazing frequency hopping thing, Bluetooth inspired technology from Hedy Lamar's work. That'd be great. You get a lot more traffic on there, but you still do always want to have that fallback. So your capacity for the airport is based on how many planes, how much time do you have to spend talking to the planes. So they wrote a system, again, in Ada Spark, this is in the talk, that would look at all the trajectories and say, are these planes going to fly into each other, or, you know, and basically figure out which planes and in what order do you need to talk with them to give them instructions to keep them moving in a way that they can successfully land, take off, whatever, without an incident. But it could identify all the planes that are like, no, these aren't going to go anywhere near each other. Don't bother spending any radio time on these planes because there's no point. But these ones, like these 12, you got to pay attention to and talk to. The other 30, whatever. So they built this system. It has been operating since they built it. I don't know, decade or two at least. Part of their contract is every 5 years, they do a training. The system has never been shut down as backup power, obviously, but just in case the backup power failed and the system shut down, they are on contract to teach them how to turn this back on, because no one, it's been turned on once and just no one remembers, no one learned how to turn this thing back on and reboot the system because it never needed to be. So it is possible to make, and I'm not going to regale you because we only have about 20 minutes left, all the other software out there, but there's quite a bit actually when you start digging of these systems that are really, really robust. And this flies right in the face. What are security best practices these days? I would say our best practices are actually symptoms. Patch all the time. Okay, but patching all the time, there's only two reasons to patch. Either your stuff's broken or you're adding features. So I don't think every patch you're applying is new features. I think most of the time it's because your stuff's broken. And the other problem with patching is when you just patch to fix an issue, you have regressions. And so when you have these really large code bases that are millions to tens of millions of lines, it's extremely likely that when you patch one thing, you might re-break something else. And there's a number of documented examples of Microsoft doing this and pushing stuff out that actually caused more problems. It fixed the issue, but now it also caused either a regression where an old problem came back or a brand new issue. The other thing you run into, as we talked about at the very beginning, kind of pre-talk here with John, is Kaseya as the most recent example. And supply chain attacks are becoming a more popular thing. Like they're happening pretty frequently because it's worth the effort. You can get thousands of high profile targets if you can slip something into the supply chain. It's a lot harder, but a lot of these groups really good. So it's well worth the effort. So because supply chain attacks are increasing, every single time you patch, if you do not have an insanely rigorous system, which I've only heard of one of these and I haven't had a chance to vet it, there's actually 6 security kernel OSs that I've actually been talking to one of the gentlemen who is on one of them. For anyone who wants to look it up, the company is AESec. They have some really good papers in their paper section, really good reading. And then the kernel they're working on is one of 6, and it's called Gemsos, the Gemini Security OS. And it's really interesting. It uses some of the techniques we're talking about with what's called a reference monitor architecture. So it has not the cyber defense triad, excuse me, the CIA triad is what we always talk about in this group. There's another one called the cyber defense triad that I should have memorized before this talk. But it's mandatory access controls and it's reference monitor. And there's one other thing I'm forgetting right now, but literally in government grade computers, you have tags, kind of like OCAP, object capability model stuff, where every bit of data, literally down to the bit level, has a tag. And there is a mandatory access control system that makes sure if something is tagged top secret, if it gets combined with secret data, well, now it inherits the top secret tag. Or if it's in a certain compartment, well, whatever just got combined with it is promoted into that compartment. Now you can't share that back down to anyone who's just got secret or anywhere that processes only secret. And this goes down to the actual processor registers can handle these tags. So again, there are computer systems out there that are lesser known that are built incredibly well. And one of the things that Jim was talking, had a nice little 1 or 2 hour conversation with a gentleman from there. And he was saying that and some of the papers too talk about how they actually ensure that software updates are not malicious. And it's more than just a good key hierarchy and code signing and all this. They actually, they have some stuff built in, and this gets into some more of the papers I haven't had a chance to finish reading yet. Can you prove software is non-malicious? Can you say, here is the expected amount of computation that I think this can and should be able to do this? Can I prove that that's all it can do before I accept the software? And there's some really interesting work there. Anyway, so I'll stop there. Both those talks, Rust, Language for the Next 40 Years by Carol Nichols, Gresham University, Correct by Construction Software. Both of these talks, definitely look them up. They should both be still up on YouTube. They're not up on YouTube, bug me on Keybase or any other way, or John. I have archived them just in case they disappear because Google's getting real good at erasing data. Well worth your time watching those. And with the last few minutes, I'm trying to leave a little time for Q&A. So we've got about 14 minutes left. Let me do 4 minutes on Copilot addressing that issue. And then we'll do a little bit of Q&A if people want. So Copilot, anyone who's not heard of this has been all over Hacker News and elsewhere. By the way, not the Hacker News. This is the Y Combinator one, since we have people that read both on here. So Copilot is a machine learning system that it looks through, and this is part of the controversy, is I didn't sign anything authorizing. I mean, I guess I signed, right, terms of service that they could do whatever they wanted with my code that's public. So they trained a machine learning model, a language generation model, on all of the code that's free that's on GitHub. And so now you can supposedly do this super awesome autocomplete, and you can just say, I need a function. What was the famous one? Carmack's function. It will verbatim, blanking on it. Carmack did a really famous mathematical function for Doom, for rendering 3D stuff. And it will actually go ahead, and if you use the name of that algorithm, it will just basically copy paste Carmack's code. So all these people are like, that's not, I mean, even if the code is licensed, if it's GNU, you might be in violation if you're not giving your code away. And someone asked Carmack, they're like, what do you think of this? They're stealing your code. And he's like, honestly, I would have given all the code away under the BSD license if I could, but I couldn't convince the investors to do that. So he's pretty chill about it, but other people not so much. They're like, that's my code. Why should someone be able to write and use my code and benefit from it when they don't even have the ability to write it themselves? And what I'll go back to here is
attribution.
Yes. Go ahead.
Without attribution.
Yes, without it. So it's kind of code washing or license washing, right? So you get the code and there's no attribution. The interesting thing there is if you misspell a function, because this is machine learning and it looks for patterns, you get buggy code. I've seen at least 2 articles about that. And it's like, oh, I hope your spelling is good. Hope the spelling in the model they trained it from is good too, because that's a problem. So that's interesting. And part of the issue with Copilot is the same issue we see with Air France 447, that disaster from the lethal software bugs, the doomsday machines talk. And when you have automation, and we've seen the same thing with self-driving vehicles, automation smooths over small issues. And that means you're not getting experience driving, you're not getting experience flying, whatever you're doing, in this case, coding, you're not, if you're just hitting tab, right? Tab, 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 and it's just filling in the code, you are not actually coding. And so then when it makes a big mistake, you have less capability to actually figure it out and find the big mistake. So Copilot, I don't know how long it's going to take people to start using this. 2 years, 5 years, I don't know. My doomsday machines talk. The ground is fertile. The seeds are planted. Careful what you ride in or fly in, because if people start using this all over the place, there's some interesting threat vectors there too. But again, I'm less interested in the threat vectors than I am with just like, wow, how many deaths can this cause? Because now we're just letting the machine program itself. But the machine is still stupid. The machine doesn't have any understanding. No one's doing, well, I won't say no one. I've seen one paper on getting symbolic computation and machines to understand concepts, not just features, but concepts. What is the abstract idea behind the symbols it's manipulating? And none of it's that. It's all just, oh, I found a pattern, and here, you know, this pattern looks like that pattern, and I can make a modification of that pattern, which is powerful in some areas. But that's not how the human mind works. It's very, very limited. If you don't have symbolic understanding and you understand the base concepts behind the stuff you're working with, your ability to synthesize anything useful is it's just not there in any meaningful way.
To me, that's the most salient point, is the people that are coding now don't understand how to troubleshoot or answer the question, why does my code do what it's doing?
Well, like, in fairness, in fairness, John, it's been that way for a while. People have been copying and pasting off Stack Overflow. This is just a more streamlined way to do it. Now, what's sad,
we're next level is the thing.
Oh yeah, and again, we're making it easier and faster. The more you reduce those barriers, reduce that damping, the worse it gets. Now, really sad here is there is a thing, if you have a powerful type system, there's a thing called hole-based programming that's super cool. It's like a really good version of this rather than the stupid version, where the program can say, well, you have a union type, you have a sum type here with 5 subtypes. And so when you go into this function, because it takes that type, it takes the union type, or excuse me, the sum type, we're going to have to do a pattern match based on which type is coming in. We're going to have 5 branches we're going to have to deal with. And there's holes in there. I don't know what you want to do with each one of those, but I do know you have to have 5. And if you don't have 5, you got a bug. If you have 4, you're missing a case. And if you have 6, you got a useless case. And so you can actually get this super advanced autocomplete via hole-based programming, where then you just fill in the hole and you say, oh, well, and then with a proof assistant, you can even have it kind of figure out mathematically, well, what would have to happen based on the type signatures? Only these functions can convert this thing to that thing. And so you actually can do, I would say, better than Copilot with a more traditional approach based on type systems without the bugs. Not only without the bugs, but if you change that sum type and you remove a thing or you add a new thing, everywhere in the code, it's going to say, oh, we have 6 that sum type is 6 subtypes now. So all these branches need an extra branch added in. And now there's all these holes, and it's not even worth compiling because now we have holes. We're missing the functionality. I need a human to go figure out how to finish the functionality, fill the hole in before we can run the code. So we've already seen better than Copilot that has no bugs. It actually reduces the amount of bugs in your code. But instead, hey, machine learning's trendy. Everyone loves AI. And so let's just throw AI at all the things, and let's ignore the fact that it is the most opaque, the most unpredictable. Like, it's so complex and opaque that you have no idea what the heck it's doing. And really depressing when you look at explainable AI and some of the explanations with like Lime. How do you know it's a husky? Oh, because the fuzz right here and the snow in the background. Really? That's how you're telling it's a husky in the picture? Probably not reliable. So anyway, let me stop there. There's other stuff I could go into, but we'll have time for stuff in the future. So are there any questions with the handful of 7 minutes we have left here? Got to give people time to type. Can always unmute.
We've got 37 people online, so several private comments that people are really enjoying the talk. So I know I am.
Oh, so I have an awesome repo. I've been trying to kind of share the wealth. I have an awesome repo, that awesome weird machines in Langsec that I'm trying to, I found a ton of links. I found like 50, 60 papers. And again, there's a whole Langsec conference that they just did at the beginning of this year. They did the 7th one. There is some extremely interesting research here. And again, like we have all the tools. If we wanted to make it where you had software you never needed to patch, you don't, because it works. And it's got a mathematical model proving that it's not going to screw up, or at least showing you exactly how and when it might screw up. Right, we could do that. We have all the tooling, and that's what I'm hoping. I don't know if Eric joined us, but I'm hoping to argue with him maybe next time. The two things that we take as just, oh, this has to be true. Humans are always the problem. And we didn't touch on that last time we had a talk, and people were disappointed because we agreed too much. We didn't cover that question. But no, it's not the humans. Tooling matters, right? Like I have a friend who's an amazing programmer, and he's like, look, I use stuff like Haskell and Idris and all this, not because I'm so smart that I can use this, but because I'm not smart enough to write high quality code without the help that I get from these systems. And there's still people coming into the industry in PHP, and Python's gaining steam like crazy. And Python, it's fine, right? It's not a bad language. It's not a good language. It's got some really weird quirks. Packaging still somehow hasn't been figured out 20, 30 years later, when every other language out there, even PHP, I think almost has better package management than Python at this point. It's fine, but the impact we're having, and with self-driving cars, I do mean that literally, we have to actually recognize that tooling matters. It's not just about ego and like, oh, I'm smart enough I don't need the help from this stupid system. Yeah, you do. You're human. You're going to screw up. It's things like 20 million lines. There's no way you fit that in your head at the same time. You will screw this up. The question is how badly. That's the only question. And you need a system that will make sure that you don't. So, and then the other thing that everyone brings up is like, well, you can't have 100% bug-free code. Yeah, it's true. It's also meaningless. Who cares? Like I will take 99.9%, bug-free code over today's stuff that's chock full of bugs. Sure, it's not 100%, it never will be, but you can get pretty darn close. And when you have systems that can go for decades without even restarting, without screwing up once, yeah, I'll take that. I'll take that all day long over the stuff we have out there that can't go more than a few hours without needing a reboot. I've actually seen people deploy web hosts where they just bounce the system every 12 hours. Oh, we have a memory leak. Okay, fix it. Well, we don't have time to fix it. We're just going to bounce we have like 20 backend web workers. So we'll just bounce those, just rotate through and bounce those everywhere. We'll just pre-allocate a few more and we'll just take them offline. Your stuff is broken. It's horrifically broken. If that's part of your actual design, the only time that I've seen something like that makes sense, the military did garbage collection, like memory collection called Collect on Crash. And they had like a 20-second flight time. And they're like, all right, just double the memory. If it takes, 5 megabytes for the flight, give it 10. And then it'll just, when it atomizes whatever it hits, done. All the memory's cleaned up. That's the only time that I've seen a strategy like that where it's like, yeah, no, that's totally valid. Like if that works, like just done, who cares? So anyway, any questions? I thought I saw a comment.
No, I think just normal chatter. Anybody else going once?
Okay, so I should reveal a little bit then with the last 2 minutes I have left. So if you are interested in these things, this place that I'm standing here, you can see we have a few computers back here. Yeah, we have a place to play. So we are not officially open yet. I have been working for quite a while to make this happen, many years. And I've been looking at how do we get the software engineering side of things? How do we turn it into real engineering? And so we have a lab. This lab will be opening, well, COVID willing. We'll see what happens with Delta and Lambda and some of the newer variants out of Brazil. But the last I heard, it will be publicly open in September. So we will see. That timeline may hold, it may not. But yeah, this lab is located at Gateway Community College. And Wyatt is handling this. He's actually been championing this and making this happen for a while. So we got a whole pile of computers. We got some gear, some donations lining up. If you have stuff that's still useful that you want to get rid of to have people play with it and learn to make better code, like again, this is different than other concepts we've seen where everyone's focusing on red teaming and pen testing. That's great. You found like, yeah, if I'm in the middle of a soccer field and I bend down, it's easy to find grass. I can do it with my eyes closed. That's great. You found holes in your pen test. Of course you did. It's not hard. Question is, can you make a system that can keep people out? So what we're trying to do is take all that rocket science in the talk, and we've actually been offered to like play with Gemsos, so that's cool. But that probably won't happen until next year, year after, because most businesses cannot meet us there. So what we're trying to do now is find the happy medium between crazy awesome rocket science like Gemsos, that's a full-on security kernel, and stuff like OpenBSD, which I have been shocked my entire time, the last 4 or 5 years in cybersecurity. Everyone's all over Linux. Linux is not that great. People forget when Linux came on the scene, BSD was already mature, already had one hell of a security track record, high performance. You had servers that had already been running concurrently for 20 plus years, and Linux was crashing constantly. The only reason Linux exists is because AT&T and SCO were a-holes, and they pulled some legal BS, and it scared everyone away. That's over finally. They have no claim on the code. BSD is made better. It's a true Unix, has actual core OS. Whatever BSD, free, net, open, I like open myself. Hardened is looking interesting, but it has an actual core that's all one team. And when they add new features and different types of privsep and different security mitigations, all of it gets added everywhere it needs to be. So we're playing with OpenBSD as our base system, and then looking at techniques we can add as layers on top of that. And the goal is to kind of nudge people like, oh, Linux, right? Good, it's better than Windows. Can we bump you now to OpenBSD? That wasn't that hard, right? Oh, I wonder if we could bump you now to maybe something like Cell4 or Certicos, and something that's even a bit more, that has a mathematical proof behind it actually will not crash. And then hopefully, eventually, we can bump people all the way into a full security kernel with a reference monitor. But, you know, we'll see. The industry's only stayed away from that for 30 years. So it's kind of insane, but that's what we're trying to do. And if you want to come build what's next, we can stop just laying more layers that aren't working and finally start moving forward in the industry. What a refreshing change of pace.